Hello, I'm Dr. Mike Jones, Managing Director of Impact Minerals Limited, and we're very excited to be involved in the CRCP research project in conjunction with CPC Engineering and Edith Cowan University. And that project is actually aimed at transforming the production of a little known but niche mineral, and one that's very crucial to the energy transition that we're going through right now. And it's also important to the development of many high-tech industries, and that mineral is actually high purity alumina, or HPA. Now, HPA is converted into artificial sapphire for use in particular in light-emitting diodes or LEDs, and these are being installed at a phenomenal rate across the globe to replace incandescent light globes, amongst many other uses. Virtually every device you have nowadays has an LED in it. HPA is also chemically inert and thermally inert, and that actually, as a result, means it has a growing use as a separator in lithium-ion battery architecture and other batteries as well. And it helps prevent thermal runaway and them catching on fire. And we've all seen pictures of Tesla cars catching on fire. And finally, there's burgeoning use in the semiconductor industry, and where HPA is used both in the preparation of certain parts of the semiconductor and also as a thermal insulator. And of course, we've all heard about the growing energy demands of AI data centers, and that is really driving growth for semiconductors, and HPA growth in that industry is growing on the back of that. So it turns out though that actually making HPA is challenging. It actually involves the removal of metals and elements at the parts per million level to produce this very pure product. And so the HPA definition is actually less than 100 parts per million of contaminants. And it turns out this is actually quite tricky and expensive to do. Companies have actually tried to make HPA, but most have failed, and that's mainly because of the nature of the feedstock they've been using and also the amount of expensive reagents that are required to actually remove those contaminants. Now, at Impact, we have an 80% ownership of a unique deposit of alumina-bearing minerals at our Lake Hope project, which is located about 500 kilometres east of Perth, here in Western Australia. And the minerals there occur in the top 2 metres of a salt lake, and they're actually very naturally very fine-grained. Most of the crystals there are at the nanometre scale, and we can only see them on a scanning electron microscope. Now, this actually offers a number of unique benefits for the production of HPA. So first, there's no on-site beneficiation required. There's no crushing or grinding of the lake mud. And so it's a very simple mining plan. We're going to dig up the lake material, stockpile it on the side of the lake a couple of months of the year, and then we're going to truck it into Perth for processing all year round. And so the process flow sheet is also very straightforward, driven by the minerals in the clay in the lake. And it's a two-stage process, and it has excellent reaction kinetics. And so as well as alumina, the flow sheet also produces us a valuable byproduct, which is potash. Now, despite this fairly straightforward flow sheet, we came to the realization that the membrane technology that's being introduced to the mining industry by Professor Amir Razmjou and his team at ECU.
Membrane technology has many applications: desalination for freshwater production, water and wastewater treatment, gas separation, and mineral processing. This is an example of a membrane module. For HPA production, we are going to use membranes for water treatment, water reuse, water recycling, wastewater management and treatment, moving towards zero waste discharge. And also we are going to use membranes for, byproduct production, and also improving the sustainability aspect of the project, potentially reducing the OPEX of the process, and also adding value to the whole project.
So we believe that membranes can help us with the quality of the byproduct, that's the potash, and there's a burgeoning demand for potash as Australia imports all of its potash. We believe we can use it to recycle the processed water and the wastewater that comes out of the process plant. And very importantly, it'll allow the chemicals that we use in the process to be recycled at a much lower cost. And so in combination, we believe that the Lake Hope deposit and the membrane technology are going to help us become the lowest cost producer of HPA globally. And that, of course, is a very exciting position to be in. We think that the research project, as a result, has got global applications. So we're looking to build on the quick start we've already made, and we have a plan as part of the research project to build a pilot plant, which includes the membranes. And that plant is going to be built by CPC Engineering, and that's going to be under the guidance of Eugenia Fegan. She's the project leader, and herself in particular and CPC have got extensive experience in engineering design, the construction of process plants, and in particular some specific HPA pilot plant experience, which is going to be crucial as we build the pilot plant. Now, once it's up and running, it's going to be the basis of all the feasibility studies that we have to build a full-scale commercial plant, which is going to be capable of being a major environmentally responsible supplier to the world's HPA market. So look, we've got a great team, a great project, and a great ambition of being the lowest cost producer of HPA globally using world-class technology.